Welcome back. Let's talk about alkylations at the alpha carbon. Okay, so we're going to start initially by looking at what you can do with a ketone, but we will take this conversation back to the aldehyde just momentarily. Okay, but just bear with me. If you take a ketone and react it with a strong deprotonated amine base and amide, um, and you do this under low temperature, you can create an enolate, a lithium enolate, and basically kind of keep it for a little while under stable conditions. Now this reaction, if done properly, can generate and turn all of the ketone into its enolate form, pretty much to completion, 100%. And the reason for that is because when you look at the pKa tables, the pKa of your ketone is 19, but the pKa of the conjugate acid of amide is 38. So the deprotonated amine or amide is more than basic enough, more than enough strong base to fully remove the alpha hydrogen of a ketone. And for that matter, it's also strong enough to do that to an aldehyde, to do that to an ester, to do that to even a nitrile. So yeah, you have a lot of options available to you if you use the deprotonated amine. Now the way that this has to be done is kind of specific, so I'm gonna kind of walk you through it for the point of view of the experiment. Pretty much what you want to do is ensure that you end up preparing the enolate in such a way that there is little to no protonated ketone, the unreactive ketone, because if there is, the enolate will react with unreacted ketone. Specifically how, I will show you in the next lecture series, but the idea right here is that yes, you want to prevent the ketone from being present in high quantities to basically have freshly formed enolate interacting with nearby ketone. And the way that you can actually ensure that that doesn't happen is that you prepare a solution of organic solvent, like some cyclohexane solvent, and you dissolve your lithium amide in there, and you have all of it dissolved in it, right? So then what you do is you set up an addition funnel. In that addition funnel, you have your carbonyl compound, in this case a ketone, and you pretty much, while keeping this under cold, so you have to do this under -78 degrees Celsius, because if you don't, you're going to end up with a mess of product. So you basically cool down. So let me kind of go back here. So you have this thing, you cool it down at -78, you set up your addition funnel, and while this remains cool at -78 degrees Celsius, you add the ketone dropwise, little by little. And the longer you take to add all of the ketone, the better. So patience is it really pays back. It's a big return on investment. Let's put it that way. So yeah, the longer that it takes you to add all of this stuff, because you're giving longer and longer intervals from drop to drop to actually be present in the solution, the better off you're going to be, because that will ensure that your ketone is never present in high concentration. And you basically do this until you have added all of the ketone in there. Now, as long as you keep this at -78 degrees Celsius, the enolate that's in there is going to remain there, and it's going to be more or less well behaved. And that's how you make that enolate, right? Now, after you have made it, the idea is that you're going to use it to introduce some type of group on the alpha position. In the previous video, I showed you that you can use this to just brominate that position, but you could also alkylate it, because technically speaking, this serves as a good, SN2 nucleophile. So if you just bring good enough electrophiles like allyl bromide, then you can definitely do an SN2 reaction. Now granted, the way that it will work is that you will reform the carbon-oxygen double bond, which then will allow the carbon-carbon double bond to become the nucleophilic portion of the molecule attacking allyl bromide. And practically speaking, the way this works out is that you basically add allyl bromide to the freshly formed lithium enolate, and then you let the reaction warm up to room temperature. It could be like half an hour, hour and a half, depends on the amount and the conditions, right? But once you've added your allyl bromide, you take the flask out from your cooling solution, and you let it warm up to room temperature, and that will allow for the alkylation to proceed to completion. So the way that this works best is if you choose your electrophiles such that they are guaranteed to be like really, really good for SN2 reactions. And three of them are allyl bromide, benzyl bromide, and methyl iodide, right? And they don't have to be bromide iodide specifically, right? But halogens, right? So allyl halide, benzyl halide, methyl halide will do the trick. Okay, so this procedure of first making the enolate to completion and then adding your substrate thereafter works really well for ketones. You can make that enolate, in pretty much full conversion, which then you can alkylate, as I just showed you already in the previous slide. This works also phenomenally well for esters. Here, if you don't use alkoxide, it is best that you use a relatively bulky amide base to prevent attack of the carbonyl carbon. But aside from that, yeah, this also works really well. You make the lithium enolate version of ester that you can react with an alkyl halide subsequently to do your alkylation. Um, this technically works to some degree, although I wouldn't recommend you to do this for every single option. But to some degree, if you use a very, very strong base like lithium alkyl, so in this case, butyl lithium, what you will do is deprotonate the OH bond first, and then the second equivalent will deprotonate the alpha position to give you a dilithiated dianionic enolate version of the carboxylic acid, which can react with methyl iodide or some of the other substrates to give you the alkylated product. Now, I wouldn't recommend you to try to do this every single time. It has kind of limited scope, so it's not always reliable, mostly because of the fact that you're trying to create a dianionic component. And not only that, right, but you're using a stronger pyrophoric substance. So if you don't have the proper setup, it might be a little more inconvenient and maybe a little less practical for you to do this. And the other reason why I also say maybe don't do it this way is because we have another method to get around this problem. If you consider your nitriles, we can basically do the same thing we did here to the ketones, to the esters. Pretty much reacted with a strong enough base. In this case, you could get away with using hydride as the strong base, which roughly speaking has the same, at least the conjugate acid of it has the same pK value as regular amine. So hydride can be used to deprotonate the alpha carbon of nitrile, give you the enolate derivative you see here. And then this enolate derivative can react with your alkyl halide to give you the alkylated version of the nitrile. Now, the thing I want to emphasize about it is that, once again, nitriles can be treated with hydronium, basically acidic media, and heat to be converted back to a carboxylic acid. So in my opinion, if you want to alkylate a carboxylic acid, I think it's better for you to turn the carboxylic acid back to a nitrile, do the alkylation, or even an ester, like that would be a better option. Turn the carboxylic acid into an ester and then do the enolate chemistry with the ester. But if you have the nitrile already at hand, then turn that into an enolate, do the alkylation, and then transform that nitrile into carboxylic acid. Like this would be the way I would recommend you to do it. All right, but all of that basically leaves us with one interesting problem, and that is that you would think that this reaction would work just as well with aldehydes. But it turns out to be the case that because the aldehydes have so much room available due to the fact that you only have a hydrogen here on the opposite end of that carbonyl hydrogen or carbonyl bond, these enolates are way, way too reactive. So reactive, in fact, that even under these conditions of like really cool temperatures and as low concentration as possible of the carbonyl present at any point in time, they're still reacting with each other, and you end up getting a bunch of many byproducts formed here. So this is not a viable form of doing alkylations of the alpha carbon with aldehydes. The way you would do that I will show you exactly how that happens in the next video. So sorry, I'm leaving you in suspense, but yeah, I don't want to make this super long. But let's save this for the next video, and we'll go from there. Bye bye.